In this video, we'll discuss the solution of linear algebra जो 2025 के नेट जून में पूछे गए थे. सो इसमें टोटल 14 क्वेश्चन लिनियर अलजेब्रा से पूछा गया था. इनमें से 6 क्वेश्चन थे 3 मार्क्स के एंड 8 क्वेश्चन थे 4.75 मार्क्स के. तो इस अराउंड 56 मार्क्स. So in this video, we'll discuss that 56 marks. So let's get started. In this video, we'll discuss the question ID this of CSIR NET 2025 जो क्वेश्चन लिनियर अलजेब्रा से पूछा गया था. And the question is saying that which of the following polynomial is the characteristic polynomial of a 2 cross 2 real matrix A such that trace of A is 7 and trace of A square is 29. So इस क्वेश्चन को सॉल्व करने के लिए we need few results जो हमें पता है. Although I'm writing it for any 2 cross 2 matrix A, the characteristic polynomial of A is t square minus trace of A t plus data of A. So this is the characteristic polynomial of A. Now the point is that trace of A is sum of its eigenvalue. As A is a 2 cross 2 matrix, I am considering its eigenvalue as to be lambda 1, lambda 2. So अगर lambda 1, lambda 2 एक eigenvalue होगा, therefore trace of A is the sum of eigenvalues, which is lambda 1 plus lambda 2, and data of A is the product of eigenvalues, that is lambda 1, lambda 2. So now we do know the trace of A, but we need trace of data of A. ठीक है ना? Again, if we are able to find out data, so we have the characteristic polynomial. So find out data हमें क्या दिया हुआ है? Trace of A square दिया हुआ है. अगर A मैट्रिक्स का आइगन वैल्यू लैम्डा 1 लैम्डा 2 है, so A स्क्वायर का आइगन वैल्यू बताए वो क्या होगा? लैम्डा 1 स्क्वायर लैम्डा 2 स्क्वायर. So these are the eigenvalues of A square, and hence trace of A square that would be equal to lambda 1 square plus lambda 2 square. Now trace of A square, which is 29, which is equal to lambda 1 square lambda 2 square. If I use the formula of A square plus B square, so I can write this lambda 1 square and plus lambda 2 square as lambda 1 plus lambda 2 whole square minus 2 times of lambda 1 lambda 2. This is equal to 29. This is equal to 7 square minus 2 times of lambda 1 lambda 2. So 2 times of lambda 1 lambda 2, this is equal to 7 square minus 29, that gives you 20, and hence the value of lambda 1 lambda 2 is 10. Therefore date of the matrix is 10, which is equal to date A, and hence the characteristic polynomial of the matrix A, if I write it, that would be क्या होगा? t square minus trace A क्या है? trace A 7, so 70 plus date A क्या है? 10. So which is our option 4. So option 4 our correct option. Thank you. In this video, we'll discuss the question ID this of CSIR NET 2025. जो question is a combination of combinatorics and linear algebra. So question बोल रहा है, let F5 denote the field of 5 elements. How many 2 cross 2 matrices with the entries in 5 have rank 1? So F5, we can consider the elements of F5 as 0, 1, 2, 3, 4, where 0 is the additive identity and 1 is the multiplicative identity. ठीक है ना? So now we need to make a 2 cross 2 matrix A, where A is like this: A11, A12, A21, A22, and where Aij belongs to F5. So how many matrices of rank 1 can be formed? ठीक है ना? So मैं क्या कर रहा हूँ? What I am doing, I am considering V1 is equal to the column vector A11, A21, and V2 is equal to the column vector A21, A22. ठीक है ना? So A is equal to, I'm just writing, A is equal to V1, V2, where V1, V2 are two column vectors. Now rank of A equal to 1, कैसे कैसे रैंक ऑफ ए 1 हो सकता है? रैंक ऑफ ए इज इक्वल टू 1 हो सकता है ऐसे, इफ वी हैव v1 0, where 0 is a zero vector, ऐसे मतलब v2 अगर 0 होगा तब रैंक 0 और रैंक 1 आएगा अगर v1 नॉन जीरो होगा। ऑल्सो अगर v1 0 होगा और v2 नॉन जीरो होगा तो ऐसे अगर इफ वी कैन एक्सप्रेस ए इन सच वे फिर भी ए का रैंक 1 आएगा, एंड ए का रैंक 1 आएगा अगर v1 v2 का रैंक 1 आएगा इफ v2 कैन बी रिटन एज सम c into v1, मतलब v1 v2 linearly dependent होगा, where c belongs to f5, definitely c is non zero। मतलब c का चॉइस क्या क्या हो सकता है, c इक्वल टू 1, c इज इक्वल टू 2 हो सकता है, c is equal to 3 हो सकता है and c equal to 4 हो सकता है। In these three cases we can get the matrix A such that rank of A is equal to 1। ठीक है ना? Now let's talk about v1। v1 is equal to a11 a12, where a11 and a12 both belongs to f5 is equal to 0 1 2 3 4। So A11 has 5 choices, A22 has 5 choices. So in such a way, how many B1 we can get? We can get 5 square number of B1s. ठीक है ना? So there are total 5 square number of column vectors can be formed by the elements of F5। Now among that हमें एक ऐसा element भी मिलेगा 0 0। So now we are not concerned about this 0 0 vector क्योंकि 0 0 लेने से हमें कुछ मतलब होगा नहीं। So we are just minus, we are subtracting 1 because of this 0 0 column। So there are total 5 square minus 1 matlab 24 non-zero columns can be formed by the elements of F5। So this case we can get 24। In this case again we have to forget 24 choices of A where rank of A is 1। Now in this case let's see, for C equals to 1 we have 24, for C is equal to 2 we have 24, for C is equal to 3 we have 24, for C is equal to 4 we have 24। So 24 into 4, so there are 96 choices। So total how many choices of A? 96 plus 24 plus 24, that gives you 144। So there are total 144 choices of A। Now let's see what is the correct option, 144, which is our option B। Thank you for watching। In this video we'll discuss the question ID this of CSIR NET 2025 जो question linear algebra से पूछा गया था। So question is saying that let X be the R vector space of all twice differentiable real valued function on 0 1, consider the linear map। So mind at this point this map is given that this is a linear map, so we do not need to check whether phi is linear or not, phi is given that it's linear map। So phi from x to r cube defined by phi of f is equal to f of 1, f dash 1 and f double dash 1, which of the following statement is true? The dimension of x by car phi is 3, car phi is finite dimensional, the dimension of x by car phi is 1, x is finite dimensional। First of all note that x contains of all twice differentiable function on 0 1, so x contains x, x square, x cube, such a way all the polynomials, right? So now this is a linearly independent infinite sets, so x cannot be finite dimensional, so we can immediately eliminate option 4। First what I am going to do, I am just going to check whether phi is onto or not। So let me clear you why I am checking that phi is onto or not। If phi is onto, if phi is onto, as phi is already given, phi is a linear map, so by first isomorphism theorem of a vector space I can say that x by car phi is isomorphic to R3, right? If I can find, if I can show phi is onto, so that's why और इसीलिए मैं पहले जो देखूंगा कि phi onto होगा या नहीं होगा। So to check phi is onto or not, first I am just taking an element ABC from R3 and I'm checking is there any f such that phi of f is equal to ABC or not, where ABC is an arbitrary element of R3। Now phi of f equal to f of 1, f dash 1, f double dash 1, this is equal to ABC or not। So I need to find a twice differentiable function f that gives 1, that gives a at the point 1, f dash 1 gives b, and f double dash 1 gives c. So that's why I'm just considering this function f of x equal to, at 1 I need to get a. So f dash 1 need to give b, and f double dash 1 need to give c. Now note that, now check, f of 1, this is equal to a, as 1 at the point 1 this vanishes as well as this vanishes. At f of f dash 1 is also b, and f double dash 1 is c. So and phi f is obviously twice differentiable function, as f is a polynomial function. So it is very much immediate that phi is onto, phi is onto. Now क्योंकि phi onto है, what I can write by first isomorphism theorem, x by car phi is isomorphic to R3, ठीक है ना. Now as x by car phi isomorphic to R3, हम बोल सकते हैं कि dimension of x by car phi is nothing but 3, ठीक है ना. So which is our option 1. So option 1 is our correct option. Thank you. Now let's solve the next question from linear algebra. The question is saying that consider a real matrix A is equal to this matrix, then what is the largest eigenvalue of the matrix A? So इस question को solve करने के लिए if you are trying to find out all the eigenvalues of A, क्योंकि एक 4x4 और अगर matrix है, so A matrix का तो 4 eigenvalue होगा. And if you are trying to find out its characteristic polynomial, then that would be a 4-degree polynomial. And if you try to find out the roots of the characteristic polynomial, that would be very complicated. So but we can bypass that process by a key result. क्या है वो result? For क्योंकि as you can see, all the elements of this elements मतलब जो नंबर दिया हुआ है A matrix का, that is they are all non-negative. अगर if you have a matrix A which is an n by n order matrix Aij, where Aij's are all non-negative, मतलब greater equal to 0, in that case if lambda is an eigenvalue of the matrix A, then mod of lambda मतलब lambda का जो absolute value है, that is less equals to maximum of sum of A 1j, sum of A 2j, sum of A nj. मतलब हर रो का अगर आप सम निकालोगे तो सम का जो मैक्सिमम होगा उससे छोटा ही होगा किसी भी आइगन वैल्यू का mod value. So in that purpose, let's find out the sum of all rows of this matrix. If you add all the elements 29, 0, 55, 17, you would get 101. Again, if you add all the elements, you would get 101. This is 101. This is 101. So what I can say that the maximum possible eigenvalue is 101. So I can eliminate option 3 and option 4. Now I am left with the two options, 101 and 67. Now now let's write down the matrix. Now let's 29 minus x, determinant 29 minus x, 0, 55, 17, 1, 28, 46, 26, 17, 28 minus x, my bad, 13, 33 minus x, 38, and 21, 67, 0, 13 minus x. ठीक है ना. If you equate that with 0, now as determinant में हम किसी भी रो को किसी भी रो और किसी भी कॉलम को किसी भी कॉलम के साथ ऐड कर सकते हैं. If you add all the columns, मतलब if you add like this, if you add all the columns in the first column, then you would get 101 minus x, 0, 55, 17, again 101 minus x, 28 minus x, 46, 26, 101 minus x, 13, 33 minus x, 38, 101 minus x, 67, 0, 13 minus x. ठीक है ना, equal to 0. So if you take 101 minus x common from the first column, in that case you can say 101 is an eigenvalue of this matrix. So इस matrix का तो 101 एक eigenvalue होगा, and that is the maximum eigenvalue of this matrix. So 1 is the correct option. Now let's move on to the next question. This is the next question. Let C0 pi be the set of all real valued function continuous function on the closed interval 0 pi for any positive integer n. Define fn is equal to C0 belongs to C0 pi is equal to this sequential function. Let f be the real subspace of C0 pi spanned by the vectors f1, f2, f3. Consider the inner product on V is given by this. Which of the following statement is true? First, they are saying that f4 belongs to this. ठीक है ना? So now for that purpose, what I am doing, f4 belongs to V का मतलब क्या है? f4 क्यों? We can write down f4 as the linear combination of f1, f2, f3, right? So let's check it out. Can we write f4 as this c3 f3? Matlab, can I express f4 as the linear combination of f1, f2, f3 or not? So if f4 is equal to this, then let's calculate inner product between f1 and f4. So this is equal to inner product between f1 c1 f1 plus c2 f2 plus c3 f3. By the property of inner product, this can be written as this is a real inner product space. I can write down c1 f1 f1 plus c2 f1 f2 f2 plus c3 f1 f3. ठीक है ना? So let's calculate the inner product between if m if n. Let's calculate it. So this is equal to integration 0 to pi 2 by pi if m x if n x dx. Now as these are the 2 points where this function are changing, so I can write down 2 by pi integration 0 to pi if mx का वैल्यू हम लिख सकते हैं sin that sin square x sin mx by sin x sin nx by sin x sin square x dx. ठीक है ना? Now I can cancel the sin square x with these two terms. So what do I have? I do have 2 by pi integration 0 to pi sin mx sin nx dx. Now this is equal to, now integration 0 to pi sin mx sin nx dx. This is equal to 0 if m not equal to n, and this is equal to pi by 2 if m equal to n. You can check that by your own. आप खुद से चेक कर सकते हो इसका इंटीग्रेशन क्या होगा. So this is equal to 0 if m not equal to n, and this is equal to 1 if m equal to n. ठीक है ना? So इससे हम क्या बोल सकते हैं? इससे हम बोल सकते हैं कि जो लेफ्ट हैंड साइड में क्या होगा, दिस इज इक्वल टू 0, दिस इज इक्वल टू 1 प्लस 0 प्लस 0 implies c1 equal to 0. ठीक है ना? In the same way I can prove c2 equal to 0 as well as c3 equal to 0. ठीक है? And so moral of the story, f4 क्या होगा? f4 0 हो जाएगा. If we can express f4 as this, then f4 become a 0 function. तो f4 तो 0 function नहीं है, which is a contradiction. So f4 does not belongs to V. So option 1 जो है, that is a wrong option. Now let's move on to the second option. The second option, first of all, note that these three f1 f2 f3 are linearly independent, as if c1 f1, if you check whether they are linearly independent or dependent, if you express c1 f1 plus c2 f2 plus c3 f3, this is equal to 0, and if you take the inner product between 0 and f1, so that is 0, and this gives you 0, not 0, c1 f1 plus c2 f2 plus c3 f3 and f1 equal to 0, that gives you c1 equal to 0. In the same way you can prove c2 and c3 equal to 0. So this f1 f2 f3 are linearly independent, so they are a basis of v. Now note that inner product between f1 and f2 is 0, f2 f3 is 0, f1 f3 is 0, and inner product between f1 f2 is 1, f1 from this inner product between f1 f1 is 1, inner product between f2 f2 is 1, f3 f3 is 1. So this is an orthonormal set of basis of v. So that's all about this question. Now let's move on to the next question. This is the next question from linear algebra. The question is saying that let a equal to ax cube plus bx square plus cx, where abc belongs to r. For f belongs to v, define q of f equal to integration minus 1 to 1 f dash t whole square dt, where f dash denotes the derivative of f. Which of the following statement is false? So we need to find out the wrong option. Option 1 is saying that q is a positive definite quadratic form of v. Option 2 is saying that q takes every positive real value. Q of x is equal to 2. Option 4 is saying that q of f plus b equal to q of f plus q of g. नाउ हमें पता है कि स्क्वायर कभी ऐसे स्क्वायर कभी को ऐसे सम में के एक्सप्रेस नहीं कर सकते. सो एज ऑफ क्वेश्चन में वी ऑलवेज वेरीफाई this option first. So let's see whether this is a correct option or wrong option. So for this purpose what I am doing, so q of f plus g, q of f plus g is equal to integration minus 1 to 1 f plus f dash t plus g dash t whole square dt. ठीक है ना? So this is, can we express this as integration minus 1 to 1 f of f dash t whole square plus g dash minus 1 to 1 g dash t whole square? I guess no. So let's take a very simple example. So let's check. For this I'm taking f of t equal to constant function 2 and g constant function x. This is more simple function क्योंकि अगर 2 लूंगा तो in this case f dash t would be 0, and g of x is again I'm taking x. So in that case what is the value of q of f? That is integration minus 1 to 1 f t f dash t, that is our 1 whole square dt. So that becoming t from minus 1 to 1, so that gives you 2. So I can again say integration q of g is also 2, but let's check what is q of q of q of a plus g. So that is integration minus 1 to 1 f dash x gives you 1, g dash x gives you 1 whole square dt. So that is integration minus 1 to 1 2 square 4 dt. So that is 4 into 2, which is equal to 8. So therefore option 4 is wrong, which is our required option. Now let's move on to the next question. Now let's solve the next question from linear algebra. The question is saying that let V be the R vector space of all polynomial with real coefficient. Let fx equal to x square plus x plus 1. Then which of the following subsets of V are linearly independent? So हमें देखना है कौन सा सबसे linearly independent होगा. This is a very easy question. So first let me write down the polynomial fx. Fx is equal to x square plus x plus 1. Now I am calculating f dash x, this all of them. Just क्योंकि पहले कैलकुलेट कर लेना ही अच्छा होगा. f of x plus 1, that is x plus 1 whole square plus x plus 1 plus 1. So that gives you x square plus 2x plus 1 plus x plus 1 plus 1. So that gives you x square plus 3x plus 3. ठीक है ना? f of x plus 1 हमें मिल गया. Now let's calculate f of x minus 1. f of x minus 1. f of x minus 1 equal to x minus 1 whole square plus x minus 1 plus 1. So that gives you x square minus 2x plus 1 plus x minus 1 plus 1. So which is equal to x square minus x plus 1. Okay. So we found f of x plus 1, f of x minus 1. Now let's calculate f of x plus 1 minus fx, which is equal to x square plus 3x plus 3 minus x square minus x minus 1. So which is equal to 2x plus 2. Okay. Uh, now let's calculate fx minus f of x minus 1. So this is equal to x square plus x plus 1 minus x square plus x minus 1. This is equal to 2x. सब कुछ मिल गया शायद. Yeah. And f dash x, the last thing is f dash x equal to 2x plus 1. Now पहला जो सेट दिया हुआ है, लेट्स वेरीफाई द ऑप्शंस. पहला ऑप्शन में f dash x equal to 2x plus 1. if x minus f of x minus 1, this is equal to 2x and 1. So you can see we can write 2x plus 1 as 2x plus 1. So this is a linearly dependent set. Now let's move on to the next option, option 2. क्या दिया हुआ है? f of x plus 1 minus fx. This is equal to 2x plus 2. Okay. Then fx minus f of x minus 1. This is 2x and then is 1. So we can write 2x plus 1 as 1 into 2x plus 2 into 1. So again, this 2x plus 1 can be expressed as a linear combination of 2x and 1. Hence, this is a linearly dependent set. The third option, fx is equal to x square plus x plus 1. f dash x we have 2x plus 1 and then we have the constant term. Now they are linearly dependent or independent, वो तो हम ऐसे देख के नहीं बोल सकते. So let's consider the linear combination. c1 into x square plus x plus 1 plus c2 into 2x plus 1 plus c3 into 1. This is equal to 0. So हम इससे लिख सकते हैं c1 x square plus c1 plus 2c2 of x plus c1 plus c2 plus c3. This is equal to 0. So अगर this is अगर if this is equal to 0, तो if we equate the like power of x की राइट हैंड साइड में 0 है, इससे हम बोल सकते हैं c1 equal to 0, c1 plus 2 c2 equal to 0, c1 plus c2 plus c3 इक्वल टू 0. इस c1 0 होगा तो c2 भी 0 होगा, इससे c1 c2 0 होगा तो c3 भी इससे 0 होगा. सो इससे हम क्या बोल सकते हैं? दिस सेट इज linearly independent as we are getting c1 c2 c3 as 0. So this is a linearly independent set. Now let's move on to the last option, option 4, where we have to verify this set. I'm just writing on the right hand side. This set is f of x plus 1. f of x plus 1 I have calculated. f of x plus 1 is x square plus 3x plus 3. Then f of x minus 1. f of x minus 1 is x square minus x plus 1. And then we have fx. fx is x square plus x plus 1. Again, this is linearly dependent or independent. वो ऐसे देख के ही नहीं बोल सकते. We need to consider their linear combination. So let's consider their linear combination. c1 into x square plus 3x plus 3 plus c2 into x square minus x plus 1 plus c3 into x square plus x plus 1. This is equal to 0. So if we take c1 common, if we take x square common, what I have c1 plus c2 plus c3. If I take x common, I have 3c1 minus c2 plus c3, and then I have the constant term 3c1 plus c2 plus c3. This is equal to 0. Again, if we equate the like power of x, we have c1 plus c2 plus c3 equal to 0, 3c1 minus c2 plus c3 equal to 0, and 3c1 plus c2 plus c3 equal to 0. Now this system has non-null solution if their coefficient determinant is 0, and it has null solution if the coefficient determinant is non-zero. So that's why let's consider the coefficient determinant 1 1 1, 3 minus 1 1, 3 1 1. So डिटरमिनेंट कैलकुलेट करने के लिए 1 1 1, सेकंड रो को फर्स्ट रो को सेकंड रो से सब्ट्रैक्ट कर रहे हैं. So if I subtract this first row from the second row, I have 2 minus 2 0. If I subtract the first row from the third row, I have 2 0 and 0. So if we express this with respect to 2, I have 4, which is non-zero. So this coefficient determinant, the coefficient determinant is non-zero, hence the system has only one solution, which is 0 0 0. So therefore this is again a linearly independent set. So option D is also correct option. Thank you. This is the next question from linear algebra. The question is saying that A and B are two distinct two cross two matrices, then which of the following option is true? Option 1 is saying that if A is invertible, then AB and BA has same minimal polynomial. So first option A. Now note that if A is invertible matrix, then AB is equal to A BA A inverse, right? So if a matrix B can be expressed as P A P inverse, where P is an invertible matrix, in that case we call A and B are similar matrix. So if A is invertible, then AB and BA are similar matrix. Similar. Now similar matrices always have the same minimal polynomial, have the same minimal polynomial. सो इससे हम बोल सकते हैं कि अगर ए इन्वर्टिबल होगा तो ए बी एंड बी ए का मिनिमल पॉलिनोमियल सेम होगा. नाउ नेक्स्ट बोल रहा है कि if 0 is an eigenvalue of a, now if 0 is an eigenvalue of a, then 0 is an eigenvalue of ab. Now 0 is an eigenvalue of a का मतलब क्या है? Date a has to be 0. Now date of ab is equal to date a into date b. So इससे हम बोल सकते हैं कि date of ab भी 0 होगा. So now as date of ab equal to 0, so 0 is an eigenvalue of ab. क्योंकि अगर किसी भी मैट्रिक्स का डिटरमिनेंट 0 होगा, so उस मैट्रिक्स का तो आइगन 0 होगा ही होगा. So therefore option 2 is also correct option. Now option 3 is saying that 0 is an eigenvalue of a and b, then 0 is the only eigenvalue of a. So ये option तो correct नहीं है. So इसके लिए I am considering an example. A is equal to एक ऐसा मैट्रिक्स चाहिए जिसका आइगन 0 होगा, 0 1 0 0. So this is a matrix whose eigenvalues are 0 and 0. Again I'm considering a matrix B जिसका भी eigenvalue 0 होगा, 0 1 0 0. So A and B are the matrices where both of this matrix has 0 as their only eigenvalue. Now let's calculate AB. AB is equal to 0 1 0 0 and 0 1 0 0. That gives you 1 0 0 0. So now note that AB has 1 as their as is eigenvalue. So if 0 is the only eigenvalue of a and b, then 0 is not the only eigenvalue of a b. That is wrong. Now moving on to the option 4. Option 4 is saying that a b and b has the same minimal polynomial, then either a and b is or invertible. Now here for the same example we are considering ba. Let's calculate ba. Ba is equal to 0 1 0 0 0 1 0 0. That gives you 0 0 0 1. Now note that the eigenvalues of AB are 1 and 0. The eigenvalues of B are 0 and 1. So therefore the characteristic polynomial of AB is x minus 1 into x, as well as the characteristic polynomial of BA is x minus 1 into x. As they are distinct factors, as they are distinct linear factors, so this is also their minimal polynomial. So AB and BA has their same minimal polynomial, although AB and BA, any one of A and B is not invertible. So option 4 is also wrong. So therefore our correct option is option A and option 1 and option 2. Now let's solve the next question from linear algebra. The question is saying that S and T such that C2 to C2 be C linear transformation and I denote the identity transformation on C2, then which of the following statement are necessarily true? So option 1 is saying that St minus Ts whole square is equal to lambda I. The characteristic polynomial of St minus Ts whole square is x minus lambda whole square for some lambda belongs to C. If St minus Ts has only one eigenvalue, then St minus Ts is equal to lambda I. If St minus Ts has the only one eigenvalue, then St minus Ts whole square is the zero transformation. So first of all, what I am doing, I am just considering the St minus Ts. I'm considering the matrix transformation of this linear transformation St minus Ts as A. So A क्या है? A St minus Ts का matrix representation है. Now as S and T both are linear transformation from C2 to C2, so A is an 2 by 2 order matrix. ठीक है ना? So if we try to find out the characteristic polynomial of A, then the characteristic polynomial of A, we already have discussed that x square minus trace of a x plus data of A. ठीक है? Now if we try to calculate the trace of A is the trace of St minus T. Now we know that for any two matrix A and B, trace of AB is equal to trace of BA. So now S and T are linear transformation, so we can also consider them as matrix. So trace of A क्या होगा? Trace of A would be 0. So क्या हो रहा है? Characteristic polynomial हो रहा है x square plus det A. Now by Caddy-Hamilton theorem, we know that any matrix satisfies its own characteristic polynomial. ठीक है ना? So इससे हम क्या बोल सकते हैं? A square plus det A into I, that gives you 0. ठीक है? So therefore what I can say, A square equal to lambda I, where lambda is equal to minus det of A. ठीक है? So therefore option A is true क्योंकि A equal to St minus T. So option A is true. Now moving on to the next option. Next option is saying that the characteristic polynomial of St minus Ts whole square is x minus lambda whole square. Now, so for the purpose, note that this option now, so characteristic polynomial of St minus T is x minus lambda whole square. Now let b equal to St minus Ta whole square, so which is equal to s square. ठीक है ना? Now observe this condition. So हम क्या बोल सकते हैं? हम बोल सकते हैं b is equal to lambda I. So इससे हम बोल सकते हैं b minus lambda I, this is equal to 0. So what I can say, b satisfies the polynomial x square minus lambda. Satisfies this polynomial मतलब sorry, x minus lambda, x minus lambda satisfies this polynomial का मतलब मैं बोलना चाहता हूँ कि x minus lambda is an annihilating polynomial of B. Now we know that minimal polynomial of B always divides its annihilating polynomial. So minimal polynomial क्या हो सकता है? Minimal polynomial क्योंकि this is a 1 degree polynomial, so this has to be its minimal polynomial. So minimal polynomial क्या होगा? X square minus lambda. Now x square minus lambda is a minimal polynomial. Therefore इससे मैं क्या बोल सकता हूँ? X is equal to lambda. That is lambda is the only one eigenvalue of B. Eigenvalue of B. Now as lambda is the only one eigenvalue of B and B is a 2 by 2 order matrix, so मैं B का characteristic polynomial क्या बोल सकता हूँ? Characteristic polynomial of B has to be x minus lambda whole square. So which is our option 2. Now moving on to option 3, st minus ts has only one eigenvalue, then st minus ts is equal to lambda I. This option is not true. For that purpose what I am doing, I am just considering मैट्रिक्स linear transformation कंसिडर करना और मैट्रिक्स कंसिडर करना दोनों सेम होता है. So I am considering the matrix A is equal to 0 1 0 0 and T equal to 1 0 1 0 0. ठीक है ना? So let's calculate ST. ST क्या होगा? 1 0 0 0 and TS. TS would be 0 0 0 and 1. ठीक है ना? Now so let's calculate ST minus TS. So therefore ST minus TS. Now option C is saying that ST minus TS has only one eigenvalue, then ST minus TS is equal to lambda. Now to solve this to check this option whether it is correct or wrong, what I am doing, I am just considering the matrix representation of two linear transformation. I am considering the S matrix 1 0 0 0, okay, and T is equal to 0 1 0 0. Now let's calculate ST. ST is equal to 0 1 0 0 and TS equal to 0 0 0 0. ठीक है ना? ST and TS मिल गया. Now let's calculate ST minus TS. That gives you 0 1 0 0. Since from this I can say ST minus TS has only one eigenvalue and that is 0. But ST minus TS cannot be represented as lambda into I for some lambda belongs to C. ठीक है ना? So option C is wrong. Now let's move to option D. If st minus ts has only one eigenvalue, then st minus ts whole square is zero transformation. So to check that, note that I already have discussed the characteristic polynomial of A. The characteristic polynomial of A is x square plus date of A. Okay. Now I'm claiming that date of A equal to 0. Date of A is equal to 0. Now if date of A is equal to lambda, which is non-zero, then the roots of the characteristic polynomial are x square plus lambda is equal to 0 or x equal to square root of plus minus lambda. Okay, so in that case I can say that A must have two different eigenvalues, but note that as it is saying that A has only one eigenvalue, so lambda has to be 0. Now if lambda is 0, then the characteristic polynomial of A becomes x square, and hence I can say that a square is equal to 0. So a square is equal to 0 representing st minus ts whole square equal to 0. So option D is a correct option. This is the next question from linear algebra, and the question is saying that T from C7 to C7 be a C linear operator with eigenvalues T minus 2, 3 and 5. Consider the subspace W equal to this. Suppose T minus 2i whole square t minus 3a whole square, t minus 5a whole square equal to 0. Which of the following statements are necessarily true? T has at least 4 linearly independent eigenvectors. Dimension of W is greater or equal to 2. Curl of t minus 2i whole to the power 2025 equal to curl of t minus 2i whole to the power 2026. T minus 2i and t minus 3i is a nilpotent operator. Now, first which is given to us. So, now first I can say that t minus 2i whole to the power 2, t minus 3i whole to the power 2, and t minus 5i whole to the power 2, this is equal to 0. So I can say that if I write a of x, so this is x minus 2 whole square, x minus 3 whole square, and x minus 5 whole square. So this is an annihilating polynomial of t. Now minimal polynomial of t always divides this annihilating polynomial. So minimal polynomial of t, if I write minimal polynomial of t, since 2, 3 and 5 each of them is an eigenvalue of t, so minimal polynomial में एक eigenvalue का तो factor होगा ही. So I can write that would be x minus 2 whole to the power k1, x minus 3 whole to the power k2, and x minus 5 whole to the power k3, where k1, k2, k3 they are all greater than 0. Why they are greater than 0? क्योंकि minimal polynomial में each eigenvalue के respect में एक तो factor आएगा ही आएगा. And I can again say that ki less or equals to 2 for all I equal to 1, 2, 3. Why? As this is an annihilating polynomial, and minimal polynomial always divides an annihilating polynomial. If there exists a I such that ki is 3, then in that case this minimal polynomial will not divide this annihilating polynomial. So k1, k2, k3 is at most 3. And if I try to write its characteristic polynomial, Ct of x, that would be x minus 2 whole to the power p1, x minus 3 whole to the power p2, x minus 5 whole to the power p3, where p1, p2, p3 are also greater than 0, and p1 plus p2 plus p3, as this is a 7 by 7 order matrix, that would be equal to 7. Now, if I try to calculate its Jordan canonical form, in it has corresponding to each eigenvalue 2, 3 and 4, 2, 3 and 5, it can have at most 2 by 2 order Jordan block. Why? As the power of the each factor in the minimal polynomial is at most 2, then it can have at most 2 by 2 order Jordan block. Now, so a 2 by 2 order Jordan block with respect to the eigenvalue 2, a 2 by 2 order Jordan block with respect to the eigenvalue 3, a 2 by 2 order Jordan blocks with respect to eigenvalue 5. Now, in this case, still there exists a Jordan block which would be of the 1 by 1 order, right? This is the minimum number of Jordan blocks. Okay, again I am saying this is the minimum number of Jordan blocks. Kyunki if the order of this is not 2 by 2, then I would have 1 by 1. In that case, the number of Jordan block will be increasing, right? The number of Jordan block थोड़ा बढ़ जाएगा. Minimum number of Jordan block तो 4 होगा ही होगा. Now, number of linearly independent eigenvectors is equal to number of linearly independent eigenvectors is equal to number of Jordan blocks. Okay, number of linearly independent eigenvectors is equal to the number of Jordan blocks. Now it has at least 4 Jordan blocks. This is the minimum number of Jordan blocks has to be 4. So it has at least 4 linearly independent eigenvectors. So option 1 has to be correct. Now let's talk about option 2. So for option 2, what I am doing, I'm just considering a linear transformation T whose matrix is of the form 2, 0, 0, 0, 0. Again 0, 2, 0, 0, 0, 0, 0, 0, 0, 2, 0, 0, 0, 0. Means I'm just considering a diagonal matrix 0, 0, 0, 3, 0, 0, 0, 0, 0, 0, 0, 3, 0, 0, 0, 0, 0, 0, 0, 3, 0, and 0, 0, 0, 0, 0, 0, 5. I'm considering these 7 by 7 order matrix. Okay. Now, if I calculate the characteristic polynomial of t, that would be x minus 2. If I write ch t of x, that would be x minus 2 whole to the power 3, x minus 3 whole to the power 3, and x minus 5. If I calculate the minimal polynomial of t, since this is a diagonal matrix, so in other words, I can say that this has to be diagonalizable. And in diagonalizable matrix, the minimal polynomial has distinct linear factors. So minimal polynomial इसमें हमें calculate करने की जरूरत तो है नहीं. I can write minimal polynomial would be distinct linear factors. So linear means the power would be 1, and distinct, so that is the minimal polynomial. As this is the minimal polynomial, this matrix has to satisfy x minus 2 whole square, x minus 3 whole square, x minus 5 whole square. Okay. Now note that t minus 5i, t minus 5i में क्या होगा? T minus 5i would be t minus 5i would be this matrix, right? SIF, that would be 0. This is t minus 5i. Now, if you calculate t minus 5i to the power k for any k, as this is a diagonal matrix, that would be k, 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 k. So, so this is t minus 5i is whole to the power k. So, in that case, now note that the rank of t minus 2i is whole to the power k is 6, as it has 6 non-zero linearly independent rows as well as columns. So its rank is 2. So hence nullity of t minus 5i, t minus 5i is whole to the power k is 1. So the dimension of w is exactly 1, which is not greater equal to 2. So this option is not correct. Again, note that t minus 2i and t minus 3i is a linear nilpotent operator or not. As for this linear transformation, this is the minimal polynomial. So t minus 2i x t minus 2i and t minus 3i, that won't be equal to 0. nilpotent operator का मतलब क्या है? t minus 2i t minus 3i, this is equal to 0. But since this is the minimal polynomial, so t minus 2i t minus 3i cannot be equal to 0. So that's all about our option 4. Option 4 is wrong. Now ऐसे क्वेश्चन में क्वेश्चन नंबर 3 सॉल्व करने की कुछ जरूरत तो है नहीं, क्योंकि इसमें मिनिमल पॉलिनोमियल का मैक्सिमम पावर 2 होगा. देन you can actually say card of t minus 2i is whole to the power m equal to card of t minus 2i is whole to the power n for all m comma n greater than 2. So as 2025 and 2026 is greater than 2, this option is correct. So that's all about this question. We are heading on to our next question. This is what our next question is. Our next question is saying that which of the following matrices are similar over R to the matrix, this given matrix. So two matrices are similar if they have the same Jordan canonical form. Okay, I'm saying it again. Two matrices over R are similar if they have the same Jordan canonical form. So now Jordan canonical form is totally depending on its minimal polynomial and characteristic polynomial. So in other word, I can say that in over R, two matrices are similar if and only if they have the same characteristic polynomial as well as same minimal polynomial. ठीक है ना? टू मैट्रिसेस ओवर आर अगर दोनों का कैरेक्टरिस्टिक पॉलिनोमियल और मिनिमल पॉलिनोमियल सेम होगा, so from that I can say that two matrices are similar. Now let's solve this question. First of all, what I am going to do, I am going to calculate the characteristic polynomial and minimal polynomial of A. So I'm just writing A is equal to this matrix minus 1 1 0 minus 1 0 0 0 0 0 0 0 0 1 1 0 1. नाउ अगर आप इस मैट्रिक्स का individually minimal polynomial or characteristic polynomial 4 by 4 order में आप if you are trying to calculate it, so आपको अच्छा खासा टाइम लगेगा और आप अच्छे खासे फंस जाओगे. So इसीलिए what I am going to do, I'll just represent A in the form of a block matrix. I can write A as A1 0 0 A2. ठीक है ना? And I'm just telling you how to deal with this block matrix. Now A1 is where A1 is this 4 by 4 block. Okay, A1 is minus 1 1 0 minus 1. What is 0? 0 is next this 4 by 4 block. 0 is 0 0 0 0. Okay, again 0 is this 4 by 4 block, and A2 is this matrix. A2 is 1 1 0 1. Okay, now let's okay, now as you can see, A is a triangular matrix. Can you see that A is a triangular matrix? So now we know that in a triangular matrix, the characteristic values or the eigenvalues are actually the elements of diagonal. So the characteristic values of A are minus 1 minus 1 1 1. These are the characteristic values of A. So if I calculate the characteristic polynomial of A, characteristic polynomial of A would be x minus or minus 1, that gives you x plus 1, again x minus or minus 1, x plus 1, x minus 1, x minus 1. So that gives you x plus 1 whole square, x minus 1 whole square. So this is what the characteristic polynomial of A is. Now the point is that I will calculate the minimal polynomial of A. Now to calculate the minimal polynomial of A, as you can see, A can be represented as a block diagonal matrix where we have two different blocks A1 and A2, and mind it, this is also a diagonal. This block diagonal matrix is diagonal where other two parts are 0. In this kind of cases, the minimal polynomial of A is actually LCM of minimal polynomial of A1 and the minimal polynomial of A2. Okay, so I'll calculate the minimal polynomial of A1, I'll calculate the minimal polynomial of A2, and I'll take the LCM. That will be the minimal polynomial of A. Now, now characteristic polynomial of A1, as you can see, A1 is also a diagonal matrix. The characteristic polynomial of A1 would be x plus 1 whole square. So what are the possible minimal polynomial of A1? The possible minimal polynomial of A1 are x plus 1 or x plus 1 multiplied by x plus 1, that is the characteristic polynomial. Now if let's check whether A1 is satisfying this polynomial or annihilating this polynomial or not. If you calculate A plus I, you won't get 0, as A plus I gives you 0 1 0 0. So A plus A1 is not annihilating the polynomial x plus 1. So annihilating polynomial, minimal polynomial of A plus 1 is actually its characteristic polynomial, which is x. Now I'll calculate the minimal polynomial of A2 in the same way. LCM, as you can see, the characteristic polynomial of A2, x plus 1 whole square, is also x minus 1 whole square. So the minimal, and again in the same manner, A2 is not annihilating the polynomial x minus 1, hence the minimal polynomial of A2 is also x minus 1 whole square. See, both x plus 1 and x minus 1 do not have any common factor, so the minimal polynomial of A is nothing but x plus 1 whole square multiplied by x minus 1 whole square, which is also the characteristic polynomial of A. Now let's check which of the given matrix has the same characteristic polynomial and minimal polynomial like the matrix A. So for that purpose, I'll jump first. I'm talking about the option 1. For the option 1, this is what our given matrix is. I'll calculate the minimal polynomial and characteristic polynomial of this given matrix. So I'm considering this matrix as B. B is equal to 0 0 0 1 1 0 0 0 0 1 0 1 0 2 and 0 0 1 0. This is minus 1. Yeah. Okay, so this is what our matrix B is. Now B is a very special type of matrix. If you look B very carefully, you will see that you can see this is an identity matrix, and all the elements over the identity matrix is 0. So, and this kind of matrix are called companion matrix. If I write a general companion matrix, let D be a general companion matrix. A general companion matrix looks like this: 0, 0, 0, 0, and the first term I am taking it minus A0, 1, 0, 0, 0, A1, 0, 1, 0, minus A2. In such a way, 0, 0, 0, 1, minus AN. This is a general companion matrix. Now, if you look again, see this is an identity matrix. Now, everything about the companion matrix is available in the Wikipedia. You can check that. For a companion matrix, the characteristic polynomial and minimal polynomial are always same. So for this matrix B, if I write down the characteristic polynomial, that is also its minimal polynomial. Now the characteristic polynomial of the companion matrix, if I calculate the characteristic polynomial of D, that is first one is x to the power n. Then if this is minus n, then an x to the power n minus 1. That would be an minus 1 as starting from 0, n minus 1, x to the power n minus 1. Then an minus 2, x to the power n minus 2. In such a way, that would be ending with a0. Okay. So this is the characteristic polynomial as well as minimal polynomial of the companion matrix. Now by using this formula, I calculate the characteristic polynomial for the option 1, that is x to the power 4. As this is plus 2, I'll calculate minus 2x square, and this is 0, this is 1. So this is the characteristic polynomial of this matrix B, CH B of x, which is equal to x plus 1 whole square, x minus 1 whole square, right? And B is a companion matrix, that is again the minimal polynomial of the matrix B. So for the matrix B, characteristic polynomial and minimal polynomial are same, and this is the characteristic polynomial and minimal polynomial of the matrix A as well. So A is similar to the matrix B. So option 1 is correct. Now let's talk about option 2. For the option 2, see, option 2 is again a companion matrix. So if I calculate the characteristic polynomial of the option 2, if I consider this matrix as C, characteristic polynomial of C is x to the power 4. So this is minus 2, so I'll take 2x square, then that is plus 1. So which gives you, sorry, minus 1. As this is plus, so I'll take, yeah, minus 1. So which gives you, this is the characteristic polynomial. So from this I can easily say that this matrix, this characteristic polynomial is not equal to the characteristic polynomial of our given matrix. So these two matrices are not similar. So option 2 is not correct. Now let's talk about option 3. Now for the option 3, the matrix is given by, if I write this matrix as E is equal to 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0. Now if you're trying to calculate the characteristic polynomial of B in our usual way, that would be very much complicated. So I'll convert this matrix E as block matrix. I'll write down this E as P I 0 P, where P is this 4 by 4 order matrix. This P is 2 by 2 order matrix. This is the identity matrix. This is now. So that gives you P is equal to 0, 1, 1, 0. Now if I calculate the characteristic polynomial of P, first let me calculate the characteristic polynomial of P. The characteristic polynomial of P is minus x 1, 1 minus x. That gives you x square minus 1. Okay. Now then the characteristic polynomial of E is actually date of P minus xi, date of P minus xi minus determinant of this matrix, which is 0. So that gives you x square minus 1 whole square, that is x plus 1 whole square, x minus 1 whole square. So that is the characteristic polynomial of the given matrix P, given matrix C, which was also the characteristic polynomial of the matrix A. So these two matrices has the same, these two matrices have the same characteristic polynomial. But now, if this matrix E has the same minimal polynomial as the minimal polynomial of A, then I can say this matrix is similar to the matrix A. So for that purpose, I will have to calculate the minimal polynomial of the matrix C. Now, again, I'll do by the block matrix term. So for that purpose, what I am doing, I am just calculating. Now, C as the characteristic polynomial is x plus 1 whole square and x minus 1 whole square. So minimal polynomial will always divide the characteristic polynomial. So the possible minimal polynomials are x plus 1, x minus 1, as minimal polynomial has the same root as the characteristic polynomial. So these two has the factors, then x plus 1 whole square, x minus 1, x minus 1 whole square, x plus 1, and the last chance is x plus 1 whole square, x minus 1 whole square. Okay, these are the possible minimal polynomial of the given matrix. Now, so for that purpose, what I am first going to do, I'll just calculate p square first. I'm telling you why I'm calculating p square. First, let me calculate p square. 1 0 0 1 1 0. So the p square is 1 0 0 1, which is our identity matrix. Okay. So e square C as the matrix p I 0 I 0 p and p I 0 p, we can calculate e square by the block matrix term. Block matrix term, what do I mean by block matrix term? Actually, if I need to multiply this row with this column, usual matrix multiplication, that gives you p square, 2p 0 p square, which is I 2p 0 I. So e square minus I is not give you the zero polynomial. So e square minus I is this not give you the zero matrix. E square minus I is 0 2p 0 0. So e square minus I and e square minus I is actually give you the zero matrix. So the minimal polynomial of the given matrix E is this, which is also the minimal polynomial of given matrix A. So this matrix E and given matrix A has the same minimal polynomial and same characteristic polynomial. Therefore, option C is our correct option. Now let's talk about option D. Option 4. Let's talk about option D. Option 4. For option 4, the matrix is given by this. Just writing down the option 4. So if I take the matrix 0 1 1 0 0 0 0 0 0 0 0 0 0 1 1 0, again we can split this matrix as a block diagonal matrix and then a block matrix. Then I'll calculate the characteristic polynomial, which is characteristic polynomial of this and characteristic multiplied by characteristic polynomial of this. If we calculate this matrix as f, then characteristic polynomial of f would be, this characteristic polynomial is x square minus 1, this is again x square minus 1, so which is x square minus 1 whole square. So the characteristic polynomial of f is as same as the characteristic polynomial of the matrix given matrix A. Now note that if I calculate f minus f plus I, if I calculate f plus I, that gives you 1 1 0 0 1 1 0 0 0 0 1 1 0 0 1 1. See, a plus I has two independent rows. These two rows are dependent, these two rows are dependent. So rank of a plus I is 2. Therefore nullity of a plus I is also 2, as this is a 4 by 4 order matrix. Therefore geometric multiplicity of a plus I is also geometric multiplicity of the eigenvalue 1 is also 2. But the given matrix A, for the given matrix A, if you calculate the geometric multiplicity, you would get 1. How? If you calculate A plus 1, A plus 1 would be 0 1 0 0 1 0 0 0 0 0 0 0 0 0 0 2 1 0 0 2 1 0 0 0 2. Okay, this is equal a plus I. See, this row and this row, this row, these three rows are linearly independent. So the rank of this a plus I is rank of a plus I is 3. Therefore nullity of a plus I is 1. Therefore geometric multiplicity of 1 is 1. But for this matrix F, geometric multiplicity of the eigenvalue 1 is 2. If these matrices are similar, then the geometric multiplicity has to be same. Therefore these two matrices are not similar. This is the next question from linear algebra, and the question is saying that let V be a finite dimensional complex inner product space for any linear map T from V to V. Let T star denote its adjoint, then which of the following are true? The first option is saying that if trace of T star is 0, then T is 0. Let V belongs to V be such that T star T of V is equal to 0, then T of V equal to 0. Suppose T equal to T star and for n greater than 1 be an integer. Let V belongs to V such that T of 2 to the power n V equal to 0, then T of V equal to 0. And suppose that T star equal to T star T for n greater than 1 be an integer. Let V belongs to V such that T to the power n V equal to 0, then T V equal to 0. Okay, so first let's see the first option. If trace of T star is 0, then T is 0. So first what I am doing, we know that trace of trace of trace of T star, this is equal to sum of all eigenvalues of T star, right? कोई भी linear transformation और matrix का trace होता है sum of all eigenvalues. Now if we consider lambda 1 lambda 2 lambda n be is eigenvalues lambda 1 lambda 2 sum dot lambda n, ठीक है ना? Now note that if lambda is I is an eigenvalue, then there exists an eigenvector which is non-zero vi such that t star of lambda I equal to lambda I vi, t star of vi equal to lambda I vi, right? So I can write t star of vi, this is equal to lambda I vi for all I is equal to 1 to up to n and vi is non-zero, ठीक है ना? Now let's calculate lambda into inner product between v and v, vi lambda I, lambda inner product between vi and vi. So this is equal to, by the definition of inner product I can write lambda I vi. Okay, so now lambda I vi, this is equal to t star of vi, t star vi vi. Now we know that for any linear operator t of v w, this is equal to v t star of w. This is what we do mean by adjoint. Uh, okay, so I can write t star of vi t star of vi, right? Now inner product of x comma x, this is nothing but norm of x whole square, right? So this is equal to norm of t star vi whole square. Again, see, this is equal to lambda I norm of vi whole square. Since vi is non-zero, then this is a non-zero real number. Then I can write lambda I, this is equal to norm of t star vi whole square by norm of vi square. So note that norm of square of norm is always greater or equal to 0. So I can say that all eigenvalues of t star is non-negative, non-negative, right? So that is, I can write lambda I is greater or equal to 0 for all I equal to 1 to up to n. But note that trace of t star is equal to 0 implies lambda 1 plus lambda 2 up to lambda n, this is equal to 0. But as each lambda is greater or equal to 0 and sum is greater than sum is equal to 0, implies each lambda is equal to 0 for all I equal to 1 to up to n. So I can say that each eigenvalues corresponding to the operator t star is 0, right? Now again note that t t star, if I take the star of this operator, so I can write t star is whole star t star, right? Now t star is whole star is equal to t star. So t star whole star, this is equal to t star. This imply t star is an self adjoint operator. Hence it is orthogonally diagonalizable, right? By spectral theorem it is diagonalizable. So we can find, therefore we can find we can find a basis v1 v2 up to vn where each vector where each vector is an eigenvector eigenvector of t star, right? Each vector is an eigenvector of t star by definition of diagonalizability. Now as then uh, since each eigenvalue is 0, so I can write t star of vi, this is equal to some lambda into vi. Now as lambda is equal to 0, this is equal to 0, so it takes each element of basis to 0. Now if you take any v be an arbitrary vector, then v can be written as the linear combination of v1 v2 vn, that is c1 v1 plus c2 v2 up to cn vn. Now if you calculate t star of v, this is equal to ci t t star c1 t star of v1 up to cn t star of vn. Now each t star of v1 0 vn 0, so this is equal to 0, and hence t star becomes the zero linear transformation. So let's see our option. First option is true. Now the second option is saying that let v belongs to v such that t star t of v equal to 0, then t of v equal to 0. Now let's calculate this. Let's check it. So the thing which is given to us is t star t of v, this is equal to 0. Now what I can write, t star t of v, if I take this inner product with the v, I would get, this is the inner product between v and 0, which is equal to 0. So I can write T star T of V V. This is equal to 0. Now, by definition of adjoint, I can write T of V, T star is whole star of V, this inner product, this is equal to 0. Now, this is equal to T of V, T of V, right, which is equal to 0. Therefore, norm T of V is whole square, which is 0. That would imply T of V has to be equal to 0, right? So, option 2 is again correct option. Now, let's talk about option 3. Option 3 is saying that T equal to T star. That is, T is a normal operator. Now, note that if T is a normal operator, then T is unitary operator, and hence it is orthogonally diagonalizable again. Now, they are saying that if n greater than 1, then be an integer. Let v belongs to b such that T of 2 to the power n v equal to 0, then T of v equal to 0. Now, the thing which is given that T is equal to T star. Hence, T is normal, then T is diagonalizable. We can find then there exists a basis v1, v2 up to vn, where each vector is an eigenvector, and I am considering corresponding to the eigenvalue some lambda I. That is, T of vi is equal to lambda I vi. Okay. Now, the thing which is given to us that if I calculate, I'm taking, let v be an arbitrary vector, then v can be written as c1 v1 plus c2 v2 up to cn vn. Okay. Now, note that T of v, this is equal to c1 T of v1 plus c2 T of v2 up to cn T of vn. Now, as T of v1 is lambda 1 v1, so I can write c1 lambda 1 v1 plus c2 lambda 2 v2 plus dot dot cn lambda n vn. Now, if I continue this process inductively, then I can write T of 2 to the power n, right? T of 2 to the power n v, T of 2 to the power n v equal to c1 lambda 1 to the power 2 to the power n v1 plus c2 lambda 2 to the power 2 to the power n v2 up to cn lambda n to the power 2 to the power n vn. Now, this is equal to 0 as this operator is given 0 operator. So, this would imply 0 equal to c1 lambda 1 to the power 2 to the power n v1 c2 lambda 2 to the power 2 to the power n v2 plus dot 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 cn lambda n to the power 2 to the power n vn. Now, from this, what I can say, note that v1 v2 vn is a basis. Now, as v1 v2 v2 vn is a basis, then this set is linearly independent. As this set is linearly independent, then each of these coefficient has to be 0. So, you can say that c1 lambda 1 to the power 2 to the power n is equal to 0. But in other words, ci lambda I to the power n equal to 0, I equal to 1 to up to n. Now, this is equal to 0 if this implies 0 if ci equal to 0 or lambda I to the power 2 to the power n is 0. That is, ci equal to 0 or lambda I equal to 0. That is, ci lambda I equal to 0 for all I equal to 1 to up to n. Now, if ci lambda I equal to 0, note that this tb, this part is 0, this part is 0, this part is 0. So, this is equal to 0, and hence option 3 is again a correct option. For the option number 4, note that t star equal to t star t So again, in the similar manner, you can show that by considering a basis of V where each vector is an eigenvector, you can show that T of V is equal to 0 for any T of T to the power n V equal to 0. So option 4 is again a correct option. So that's all about this question. Now we are moving on to the next question. The next question is saying that let B of VB be a non-degenerate symmetric bilinear form of R2. Let Q of V equal to B of BV be the corresponding quadratic form. Suppose there exists a vector VW belongs to R2 such that B of VV equal to 0 and B of VW is non-zero. Which of the following statements are necessarily true? So first option is saying that B of WW equal to 0. Second one is saying that there exists A belongs to R such that Q of AB plus W equal to 0. There are infinitely many alphas such that Q of alpha B plus W equal to 0 and Q is equivalent to the quadratic form Q of xy equal to x square minus y square. Now, first, I'm just saying few results related to the quadratic form and non-degenerate symmetric bilinear form and respective is associated quadratic form. Now, if Q of xy be the quadratic form and its associated matrix is A, then B of VW means B is nothing but V transpose A W, where A is the associated matrix of Q. Okay. Now, first, let's talk about option 1. So, first, what I am doing, I'm just taking Q of xy. This is equal to x square minus y square. Okay. Now, then its associated matrix is, as this is a quadratic form, its associated matrix is 1 minus 1 0 0. Okay. Now, what are they saying? There exists a V such that uh, B of VB equal to 0 and but Q of B of VW is non-zero. Now, note that uh, Q of, if we choose V equal to 1 1, then Q of V, this is equal to 1 minus 1, which is 0.